Hi everyone, in today's lesson we're going to talk about types of discontinuities. First, we need to define what continuity is. So a function is continuous if you can trace over the function without picking up your pen or pencil. So for example, this function here, the sine curve, it's smooth, right? I don't have to pick up my pencil to follow the curve. Same thing with this linear function. I don't have to pick up my pencil to trace the curve. And same thing with this polynomial function here. Now, that's not a real textbook definition, but don't really stress about the textbook definition until tomorrow. Today's goal really is just to understand that a graph is continuous if you don't have to pick up the pencil to trace it. Now, discontinuities. What is a type of discontinuity? Well, let's just take a look here. You see here how we have a parabola looking thing, right? But we have a hole here. So if you were to start tracing, trace, once you reach the hole, you have to pick up your pencil, jump over the hole, and then continue your tracing. So whenever you have a hole, it's called a removable discontinuity. So here's an example of a rational function that has a hole. So again, you trace, you pick up, and you go back down. Another type of discontinuity is an infinite discontinuity, or where there's a vertical asymptote in the graph. So we're tracing our curve, and we've reached the asymptote. We have to pick up our pencil so that we continue tracing on this side. So here's another example here. This is an example of a rational function that has both. This has a vertical asymptote here and a removable or a hole here. So there's two spots where you'd have to pick up your pencil. You'd have to pick it up here over the hole, and then here over the vertical asymptote. And last but not least, another type of discontinuity is a jump discontinuity. So again, we're picking up our pencil, we have to jump to get to the other piece. Doesn't really matter about that open or closed circle, it's really about the jump to trace over here. Same thing over here, this is an example of a piecewise function. We're tracing, oh, we're jumping, and we're continuing on, okay? So the goal of this back part of the lesson is really to be able to determine discontinuities algebraically. So you could be given something like this, or the example below. And you could be asked to determine where each function is discontinuous and state the type of discontinuity. Now, I've taken the liberty of putting the graphs here for visual representation, but the visual will not be there for you. It will just be the graph. So just the equation. So let's just look. Here is a rational function, and here's the graph of the rational function. You should look at this and notice that there are two types of discontinuities. We have this vertical asymptote here, and we also have the hole here. So if we see that we have those two types of discontinuities, right? We have a hole and we have our vertical asymptote. How would we do this algebraically? Well, it's very simple. The first thing you would do is factor. So the numerator we can't factor, we leave that as x plus 2. And the denominator we can factor using am, so what numbers add to negative 2? That multiplied to 8. That answer is x minus 4 and x plus 2. Now what you notice when you factor is that these x plus 2's are going to cancel. So maybe we should change step 1 to say factor and simplify. And like we discussed, it's clear that these two cancel, but you have to be careful to put a placeholder of a 1 on the top because there's nothing left over there. So if we simplify this, we get 1 over x minus 4. So now this information here, this factoring and simplifying, actually gives you the hole and the vertical asymptote. So the thing that is being crossed off is your hole, and the thing that's left over on the bottom is your vertical asymptote. Now, how do I know exactly what the hole is? It comes from that undefined piece. So if you were solving for roots of the denominator, you would take your x minus 4 and x plus 2, and you would set it equal to 0. These are what we call undefined values. That's where the denominator is equal to 0. So if we did a little baby chi chart, we would get that x equals 4 and that x equals negative 2. So when you're finding your hole and your vertical asymptote, you're actually going to use these values, not the actual like x plus 2 or x minus 4. So technically this hole, since the x plus 2 canceled with this x plus 2, my hole is at x equals negative 2. And my vertical asymptote here, since it came from the x minus 4, really is x equals 4. So if we were going to write this out, my vertical asymptote is x equals 4, right? Vertical asymptote is x equals 4. So that proves here, right? Vertical asymptotes are up and down, vertical, x equal equations, x equals 4. So that is the first type of discontinuity. And now the second type of discontinuity is at your whole. So remember, since the x plus 2 is canceled, our whole is at x equals -2. It's pretty much the opposite sign of what's in the parentheses. And that's clear. We have our -2 is our whole. But really a whole is a point. So we need to find the y value of this point. We have the x value. So we have that x is -2. We must find the y value. And the way that you do that to find the y value of the whole is you plug your x value of your whole, -2, into this simplified equation. And the reason why you need to use the simplified equation is because if you used the original equation, your value would be undefined and you would get 0 on the bottom, right? If you plugged in -2 in here without crossing it off, you'd have -2 plus 2, which would be 0, and that wouldn't work in here. So we must use the simplified equation. So we have f of x equals 1 over x minus 4. So f of x is the same thing as saying y. So y equals 1 over, and instead of x, I'm going to put -2 and then minus 4. So the y value, if we do some quick math, is 1 over -6, or simply -1/6. And that's it. Now, obviously on here, you can't really see that this y value is at -1/6. That's why we do it algebraically. It's a little bit too tight here. So again, that's how we find a vertical asymptote and a whole. All right, let's take a look at the second example. I'd actually like you to pause the video and try to see if you can do this second example by yourself, and then hit resume when you're ready for the explanation. Okay, so the first thing I did was I factored my numerator, and I got x plus 3, x minus 1. And my denominator I leave alone, excuse me, and I get x plus 3. Now I notice that these x plus 3's cancel, and I can simplify this thing to simply x minus 1. Now, I don't need a placeholder on the denominator here because technically anything divided by 1 is itself. If you want to put it, you can, but you don't have to. So if we understand from before, we've crossed off the x plus 3's. So the opposite sign is the whole. So I have a whole at x equals -3. Now, notice that there's no other term in the denominator. That means there's no vertical asymptote. Just because there's something in the numerator doesn't mean that becomes the vertical asymptote. We get wholes and vertical asymptotes only from the denominator, nothing from the numerator. So in this example, we only have a whole, which is clear from this graph. We see that I have my whole here at -3. The y value is -4. Let's prove it. So remember, so I guess we could write down there's no vertical asymptote. And we have a whole at -3 is my x value. And how do I find that y value again? We're simply going to plug into the simplified equation. So y value, and my simplified equation is this guy right here. So we're going to just say y instead of f of x equals -3 minus 1. So my y value is -4. So -3, -4. So here we go there. That is my whole. And that proves here is my whole. Okay, let's take a minute now. And why don't you try the third one? And then pause the video and hit resume when you're finished. Okay, so what you should notice about this one is that there's nothing to factor. You can't factor the top, you can't factor the bottom. And from this picture, it just looks like a straight line, which if you trace it over with your pencil, you don't need to pick up anything. So this one, there is no discontinuities. So we can just say no discontinuities. And you can say this function is continuous. And the real reason is because it's a linear function or because it's a line. So this function is continuous because it's a line. All lines are continuous. There's no holes in them. The reason why we're getting a hole in the second example is because we have a rational function, rational meaning fraction. The reason why we have a hole and a vertical asymptote in the first problem is because it's a rational function. If we have a fraction, there's a possibility for there to be these holes and asymptotes. Now, how do we prove this is a line? Well, we can just take a look at the equation and we can put it in y equals mx plus b form. We can divide this and this, and then we can divide this and this. So our line, f of x, is in the form 4x over 2, we're dividing everything by 2, and 5 over 2. We can even simplify that further. 4x over 2 is 2x plus 5 halves. So this is my line in the form mx plus b. So I just wanted to keep you on your toes on that one so that you understood that not every single fraction is going to be a rational function where you will have holes and vertical asymptotes. All right, that's really it for today. If you have any questions, now's a good time to jot them down. Otherwise, I will see you in class tomorrow. Have a good night.